I set up a Horner-Wadsworth-Emmons reaction. The reaction allows the stereoselective olefination of aldehydes or ketones using stabilized phosphonate carbanions. Phosphonate carbanions are more nucleophilic than the corresponding phosphorus ylides, allowing them to react with a wide range of aldehydes and ketones under milder conditions. Hindered ketones that are typically unreactive in Wittig reactions can react in Horner-Wadsworth-Emmons olefinations. The reaction favors the formation of alkenes. When electron-withdrawing phosphonates are employed, the elimination of the oxaphosphetane intermediates accelerates, boosting the production of Z-alkenes. This is known as the Gennari modification. In addition to the type of phosphonate used, the selectivity of the reaction can also be influenced by other factors such as the choice of base and solvent. For more details, check out the Chemists Cookbook. To set up this transformation, I needed to use an aldehyde or a ketone and a phosphonate. However, the phosphonate I needed was not commercially available, so I had to synthesize it. How could I prepare it? Luckily, the preparation of starting alkyl phosphonates is possible using the Arbuzov reaction. The Arbuzov reaction allows the reaction of a trialkyl phosphide with an alkyl halide to yield an alkyl phosphonate. To get the alkyl halide, I just needed to synthesize the alpha bromoketone from a commercially available ketone. There are several protocols and conditions to set up this transformation. Bromination with NBS is really convenient because N-bromosuccinimide is a white solid compound that is very easy to handle. However, the reaction produces a succinimide byproduct that might be difficult to remove, and I didn't want to purify the product after the reaction. On the other hand, bromination with bromine is slightly less convenient because bromine is a volatile, dark red to brown liquid and is very reactive. Since I had previously made a video on a bromination reaction using NBS, I wanted to try the reaction using bromine. This transformation is usually carried out in acetic acid, but I found another procedure using diethyl ether. Into a round bottom flask, equipped with a magnetic stir bar and charged with 2 grams of my liquid ketone, I added 14 milliliters of diethyl ether. According to my calculations, I was supposed to add 1.8 grams of bromine. Considering the high density of bromine, 3.1 grams per milliliter, I needed to add 580 microliters of the reagent. I was going to use a micropipette, but I thought it wouldn't be a good idea. Searching on the internet, I found that using a disposable syringe with a white needle would do the trick. I tried to be quick and accurate at the same time, but measuring 580 microliters was rather complicated, so I decided to aim for a slight excess and add about 600 microliters. I don't know if that was the best way to add the reagent, but it turned out pretty well. Anyway, if you have other ideas, please let me know in the comments. After the addition was complete, I allowed the mixture to stir at room temperature. In the meantime, I quenched the bromine remaining in the needle and syringe with a saturated aqueous solution of sodium thiosulfate, which is a reducing agent. After 5 minutes, the bright red color of the reaction mixture gradually faded into a light yellow color. According to the mechanism, the enol form of the ketone reacts with bromine to give the alpha halogen substituted product and hydrogen bromide. So it was fair to assume that the reaction was complete within the first 5 minutes. However, I checked the reaction progress by TLC, and despite using several solvent systems, I could only see a single spot with the same retention factor as the starting material. After a while, I decided to prepare a sample for UPLC analysis. My compound was not ionizing well, so I couldn't find the mass of my product or the typical bromine pattern. But it was UV active, and I could easily identify my starting material and the formation of 2 products, the desired product and the dibromoketone. According to the NMR I measured on the crude residue I obtained after working at the reaction, there was a peak at around 5 ppm corresponding to the 2 protons of the ketone. There was also a small signal in the aromatic region corresponding to the proton of the dibromoketone. There were no peaks around 2.5 ppm, indicating the absence of a starting material. I quenched the reaction with sodium bicarbonate, and the mixture started bubbling as the base reacted with the hydrogen bromide generated during the reaction. I then extracted the aqueous phase with the ethyl ether, and I rinsed the organic phase with aqueous sodium thiosulfate to quench any remaining bromine. I dried the organic layer with sodium sulfate, filtered it through a cotton plug, and evaporated the solvent to obtain the crude product in quantitative yield. I finally got 2.8 grams of a light yellow oil that I used directly in the next step. The next step was the Arbuzov reaction. I dissolved the crude residue in 25 milliliters of acetonitrile and added 2.5 equivalents of trimethyl phosphate. I refluxed the mixture overnight. The following day, I analyzed the reaction mixture by UPLC. This time, the product ionized well, and according to the given mass, I identified this peak as my desired product and this other peak as the byproduct generated from the reaction with the dibromoketone. All the starting material was fully consumed. I let the mixture cool down to room temperature and evaporated the solvent to obtain a crude product. I then purified the crude product by automated flash column chromatography. I dissolved the crude residue with a minimal amount of DCM and loaded it directly to a previously equilibrated column, which was packed with the stationary phase, in this case, silica gel. I then established the mobile phase with a gradient of cyclohexanes and ethyl acetate and hit the play button. As the reaction products started to elute, I modified the gradient to make the eluene more polar by increasing the percentage of ethyl acetate. This would push the elution of the more polar components remaining in the column. As the different compounds were detected by the UV-Vis detectors, the eluted fractions were collected into separate tubes. I analyzed the different fractions by UPLC and combined the tubes containing a solution of my desired product in a round bottom flask. After that, I evaporated the solvent and obtained 2 grams of a white solid. This was the phosphonate, which I obtained in 65% yield over 2 steps. The yield was good, but I think it could be improved if I use slightly less bromine in the first step. A slight excess of bromine helps ensure complete reaction, but too much leads to dibromoketones. To make sure I got my desired product, I prepared a sample for NMR analysis. I added 0.6 milliliters of deuterated chloroform into a vial. With a Pasteur pipette, I took a few milligrams of my product and dissolved them in the chloroform sample. Then, I transferred the solution into an NMR tube and locked the sample in the NMR spectrometer. Analyzing the NMR spectrum, I identified some additional peaks. I was planning to repeat the purification, but I could only see a single spot on the TLC plate. So I prepared another NMR sample using deuterated DMSO. This time, the analysis suggested the product was highly pure. Probably, the product isomerizes in chloroform to give the enol tautomer. In the NMR spectrum, I could see a doublet that integrated for 6-methyl protons with a coupling constant of 11 Hz, due to the coupling with phosphorus. The coupling constant of the methylene protons was almost 20 Hz. The final step of the synthesis was the Horner-Wadsworth-Emmons olefination. For this transformation, I found many different conditions using different bases, solvents, and temperatures. So I decided to set up 2 trial reactions. Into a pressure tube charged with a magnetic stir bar and loaded with my previously synthesized phosphonate, I added DMF under an argon atmosphere. I then cooled the mixture to 0C and added sodium hydride in one portion. In the other tube, I dissolved the phosphonate in THF and added potassium terbutoxide. After stirring for 15 minutes, I added a solution of the ketone dissolved in DMF and a solution of the ketone dissolved in THF in the second tube. After that, I replaced the ice water bath for an oil bath and allowed the reaction mixture to stir at 80 C. The reaction in THF was stirred at 60 C. I also sealed the tubes. But then, I recalled a paper I read some time ago about the explosion hazards of sodium hydride in DMF due to the thermal instability of this mixture. So I decided to add an argon balloon to release some pressure. I didn't take more precautions because it was a relatively small scale, but I would definitely not recommend this system in a large scale setup. I monitored both reactions by UPLC, but after a few hours, there was very low conversion of the starting material. After overnight stirring, the conversion was still low, so I decided to leave it over the weekend. The reaction was really slow. It was disappointingly slow. I think I should explore additional reaction conditions to try to optimize the reaction before scaling it up. Bye.